We have our nice B field in our inductor. Now let's discharge the RL. So let's look at the circuit again. It was like this. The battery caused current to flow. We reached a steady state where there's nice current going through the inductor. We have a nice B field now inside the inductor, but it's constant. So there's no back EMF. All the potential drop is across the resistor, and everyone is happy. Now, if we open the switch like this, this is no longer powering this current. You got to have the battery doing it because we're losing energy here. The current is flowing through the resistor. So this will affect the circuit, but it makes a lot more sense to analyze it if you have a loop. So usually you draw another line like this, and the switch can go between the battery and just having a closed loop like that. So this is what we're doing now. We still use Kirchhoff. We still think of the current going this way. We're going to analyze it this way. We're going to write essentially the same Kirchhoff loop rule, just without the EMF. So this is how we discharge the RL. And of course, discharge is not the right word. That's the word when you're using a capacitor, because you're taking the charge off the capacitor plates. For an inductor, I don't really know what the word is. There really isn't a word. You're turning the field off. I'm gonna create the word. You're discombobulating. There you go. We're going to discombobulate the RL. It's all, okay. And it's got a B in it, so there you go. Okay, so to discombobulate it, we're going to apply the Kirchhoff rule. Like we just said, we're going to say minus IR, because we're going clockwise around the loop, and minus L di dt, because we know that's what an inductor does. It has a back EMF, equals 0. And now we're back to our differential equation tricks that do not require substitutions. Let's see, we're going to bring this over here, and we're going to get di over I on one side, and then we're going to end up with minus R over L dt on the other side. And we integrate both sides like that. So integrate this side, integrate that side. And now we need these boundary conditions. We need to say that we had, at time t equals 0 is when we flip the switch. So at time t equals 0, we had some current. Okay? We had a current I naught. So we would say the time, at 0 we flip the switch, and we want to know what's happening at some later time t. And at time t equals 0, we had I naught, some initial current, and we just want to know what happens to that current. So it goes from I naught down to some current I, like that. All right, well, now we just have to integrate both sides. So this, we've done that integral a few times. It's the natural log of I evaluated from I naught to I. And this one is minus R over LT evaluated from 0 to t. And we've seen this before. This is the natural log of I over I naught equals minus R over LT. And then we take e to this and e to this. And you get that I equals I naught. So this becomes I over I naught. Take it to the other side. Equals e, I naught e to the minus R over LT. So you find that it undergoes basic exponential decay. If we were to plot versus time and plot I, it starts at some value I naught, and it just makes its way to 0. That value I naught, you can look at it and realize, oh, well, when I first flipped it, the current was running as though the inductor weren't even there. All this potential drop was gone, so the current is just the EMF over R. I naught is the battery's EMF over R. So as the current dies away, the magnetic field goes away, there's no dissipation in the resistor, and it just goes, everything goes to 0.